Hello, everybody. Hi, thank you for joining us today. My name is Jen McConnell, and I'm the product manager here at Protochips. And this is our 6th installment in this webinar series that we're doing called Electrochemistry in the TEM. I'm really excited about today's speaker. We have a wonderful speaker who's our first in the series that's got a background in corrosion research. Our previous webinars in the series have been focusing on batteries and catalysis, but corrosion of steels and alloys has had quite a growing interest for in situ TEM. And today's presenter is going to talk about a new technique that will make it easier for these types of results in the TEM to be incorporated into a grander research scheme with confidence and with relevance. You'll find the previous webinars that I mentioned on our YouTube page, or you can go to the webinar page on our website that's linked in the chat. You can find them linked there as well, or you can reach out to us via the webinar email that you got for joining today. We also have a few remaining webinars in this electrochemistry in the TEM series. Like I said, if you go to that link in the chat, you'll see them and you can go ahead and register so that you don't forget and you don't miss out. So just a couple of housekeeping items before we get started here. Because we have such a large attendance, we're going to have everybody muted just to make it easier for listening and for hearing the speaker. So if you have questions, there is a questions box. If you could please enter them in there, and at the end of the webinar, we'll be doing a Q&A session where you can, if we've got time to get through all of them, that's great. We've had a lot of questions in the past, and so sometimes we'll just go ahead and connect those who don't get answered with our speaker, and then he'll be happy to answer offline for you. And then if you don't mind, there's going to be a very short survey that pops up at the end of the webinar. If you could just fill that out real quick, that's going to help us in the future. We would really appreciate that. So let me introduce the star of the show today, because it's certainly not me. We've got Dr. Sanjay Choudhary here today. Sanjay is from Raipur, India, and he's currently a postdoctoral research associate with Professor Robert Kelly in the Department of Materials Science and Engineering at the University of Virginia here in the US. He's studying localized corrosion characteristics of aluminum alloys and stainless steels using in situ TEM and finite element modeling. Prior to joining UVA, he obtained his PhD from Monash University in Australia under the supervision of Professor Nick Birbilis, where he studied the evolution of passivity in chromium-containing alloys, including stainless steel and high-entropy alloys using in situ spectroelectrochemistry, which involves real-time composition analysis of the electrolyte during electrochemical testing. Sanjay, we're really excited to have you here. Looking very forward to your presentation today. I'm going to pass it to you, and you can take it away when you're ready.
Thanks, Jen, for this kind introduction, and thanks a lot for giving me the opportunity to present my work here. And to all, good morning, good afternoon, and good evening if you're joining us from different time zones. So before going through the work, I would like to thank my supervisor, Professor Robert Kelly, for continuous support and guidance, and also for giving me the opportunity to work on this fantastic problem. And thanks to the whole team of Protochips, especially Jen, Mike, Kate, and Tim for this fabulous collaboration, and to DARPA for funding this project. All right, so let's start with the term corrosion. It is now well known that most aqueous corrosion phenomena are electrochemical in nature, which involves oxidation of the material and reduction of the electrolytic species. But the corrosion mechanism and associated electrochemical reactions differ from material to material, or if you change the electrolyte. For example, it could be either active uniform dissolution, or it could be localized dissolution, also known as pitting or crevice, or it could be selective grain boundary dissolution. So how do you know the operational mechanism? Well, if you take a piece of corroded structure, and after rigorous failure analysis characterization, you might be able to figure it out. Or you can do a simple electrochemical test. And information what you're going to get from your electrochemical testing can help you predicting the corrosion mechanism as well as the corrosion rate even before using the material for the application. All right. So how do you do electrochemical measurement? Well, first, you can measure the surface potential. And if you know the chemistry of the electrolyte, you might be able to figure it out whether the material is getting corroded or it is in passivating condition. But potential cannot give you any information about the kinetic. So for that, you need to polarize the specimen, and based on the corrosion mechanism, you will have different electrochemical response from the material surface, and that is how you will be able to figure it out, the corrosion rate as well as the corrosion mechanism. Now the question comes in that how do you measure the surface potential even during free corrosion or during polarization test? Well, measurement of absolute potential is not possible. What you can do is you can measure the potential difference between two surfaces. It means you need to have an additional interface with relatively stable potential, and that's where the reference electrode comes into the picture. Most of the commercial reference electrode, they use redox couple in equilibrium with the surface, so that fixes the potential of reference electrode. Another characteristic you need in an reference electrode is it should be non-polarizable. What does that mean is if you apply a small amount of current to reference electrode, its potential should not be changing. Because in theory, when you are polarizing the specimen, a small current, which is in range of picoamp, do pass into the reference electrode. So here is an example of sintered AgAgCl electrode. Here what you can see is change in potential of the electrode. If you apply a 0.5 milliamp per centimeter square, which is a huge current, the change is very small. It is almost around 11 millivolt. And as I said, in reality, the current which goes into the reference electrode is in picoamp, so you will not see any difference in the potential. All right, but now that you need a redox couple, you need to have an isolated system. It means most of our commercial reference electrodes, they look like a glass tube, and it has a porous frit at the end, which allows ionic conduction, but it does not allow mixing of the solutions, I mean the reference solutions and whatever solution you are using for your study. So that helps protect the equilibrium in reference electrode. And if you are worried about the IR drop in the solution, or if you need better sensing properties in reference electrode, you can use something called Luging probe, which can act as a salt bridge. So yeah, so this is a short summary of reference electrode. But now, because of all this requirement, the size of most of our commercial reference electrodes are big enough that they cannot go inside a TEM holder. So now the question is then, how does liquid cell TEM works? Well, here is an exploded view of the product made by Protochips. So the most important part is the E-chip, which has 3 electrodes all made of platinum. And working electrode is the place where you weld your FIB sample, and other 2 electrodes serve as the reference electrode and counter electrode. But well, platinum as reference electrode is not a good idea. Why? Because first, it is polarizable, so a small amount of current can change its potential. And second, we don't have any thermodynamic database with platinum. And every time you use different electrolyte, you have different potential of platinum. So it gives us a lot of problem. So now the question is, how do we use the true reference electrode in our liquid cell TEM experiments? Well, there are a couple of ideas. So researchers from Japan, they used little longer flow tube, electrolyte flow tube, and they used a true reference electrode outside the TEM holder. As you can see schematically here, that is a clever idea. And the second idea, which we were particularly interested in, is something called leakless reference electrode. Researchers from University of North Carolina, they replaced the porous frit with just a metal wire. This is a fantastic idea because now if it works, then we can just connect that metal wire tip into put that metal wire into the TEM holder. But it turns out in both the cases we get potential offset, or I would say the potential what you measure is considerably different than what you measure with your commercial reference electrodes. All right, so it is not helping. Now with the concept called bipolar electrochemistry, we came up with the idea something called metallic Lugin probe. So let's see how does it work. So here is our conventional setup, all 3 electrode in 1 beaker. But what we decided is to have a separate beaker with same electrolyte, of course, and put our reference electrode in the separate beaker and use a metal wire as bridge between these 2 beakers. So here you can see the schematic of our setup. Someone might say that this is a crazy setup. How does it work? Well, first question is, does it work? Right. So all right. So here is a beautiful CV, cyclic voltammetry curve of platinum in acidic ferric ferrous solution using our conventional setup and using AgGCl reference electrode. If you use platinum as reference electrode, there is no difference in the shape, but you can see there is a significant shift. And now, instead of using platinum as your pseudo reference electrode, if you use it as a metal bridge, you get exactly identical result as what you get in your conventional setup. So this is crazy. Now let's see what is the effect of the scan rate. So here are the CVs of platinum with respect to with different scan rate. And it turns out if you use our metal bridge setup, you get exactly the same result. This is great. Now, what about the characteristic of the wire? Again, it turns out there is no effect of the exposure area in both ends of the metal bridge or the length of the wire. So this is crazy. And what about the platinum? Is platinum as metal bridge a special condition? Turns out no. You can use any metal wire for your metal bridge experiment. Here what you can see is we used 5 different metal wire, copper, tungsten, zinc, and stainless steel, and the curves are on top of each other. All right, so it is working perfectly with our beaker experiments. But now what about the liquid cell TEM experiment, right? Let's see. So here is a CV of platinum working electrode using platinum reference electrode, what is already there in our liquid cell TEM setup. And if you use, instead of using platinum as your pseudo reference electrode, if you use it as a metal bridge, you get exactly the result what you want to get. So yes, it does work with liquid cell TEM as well. So now, just to clarify how to use this setup. So this is what you have with the liquid cell setup. The cables are coming out of the TEM holder. You connect it to the cables of potential state. But with our metal bridge setup, what you have is in between you have an additional beaker with our commercial reference electrode, and use another piece of platinum wire which will be connected to the reference electrode alligator coming out of the TEM holder, and put it in the beaker. So this is a simple experiment, and it is really effective. It does work, and we have done multiple experiment to confirm that it is giving us exactly the same result what you want to get, what you get with your conventional setup. All right. So the platinum bridge concept is really good, and we went bananas with the setup. And so here are some more results with standard electrochemical corrosion tests. So first graph you see is potentiodynamic polarization curve of stainless steel in substitute ocean water. And you can see with conventional setup or using the metal bridge setup, the results are on top of each other. No difference in pitting potential or repassivation potential. The second graph is electrochemical impedance spectroscopy of magnesium in substitute ocean water. Again, almost identical result, except there's a slight bit of shift at high frequency. And now that we know that we don't need to worry about the size of the wire or the exposure area of the wire. Now you can run an electrochemical measurement in a small drop of electrolyte. As you can see here, the graph shows the open circuit potential of stainless steel in a substitute ocean water drop, and the result is almost comparable to what you get with your bulk electrolyte setup. All right, so the metal bridge concept is working almost everywhere. Now the question is, how does it work? Okay, so let's see here. So here is our conventional setup. In one beaker, you have your working electrode as well as your reference electrode, and these two electrodes can be considered as two batteries. And what we are measuring is the potential difference between these two batteries. And if you have a metal bridge setup, then you are introducing two new interfaces, and you can arrange these batteries in a way that there is no current flow, and then it will give you a simple yet really effective equation. So from this resulting equation, what you can see is you have an additional term, which you can call it a potential offset, and which is basically the potential difference between two ends of the metal bridge. So yes, the concept works if that potential offset is zero. In other words, if the potential of metal bridge in both the ends is same, then you will not have the offset. And well, if you're using the same electrolyte in both the beakers, and if you're using only one metal wire, then in theory you should not be having any potential offset, and that's why you can use any metal wire as your conducting metal wire as your metal bridge. All right, let's go a little deep into this concept. So here is a result showing open circuit potential of platinum working electrode when you are changing the ratio of ferrous to ferric in 0.1 molar HCl. This result can also be predicted using Nast equation. So this is great. And if you are using our metal bridge setup, you get exactly same result. So yes, but yes, when you are using same electrolyte in both the beakers. But what if you decided not to change the electrolyte of your reference beaker, and you are only changing the chemistry of your working electrode beaker? So here is the result. It turns out you are getting same potential irrespective of the electrolyte chemistry in your working electrode beaker. That is weird, except it is not. So let's see our equation here. And because we are using platinum for your working electrode as well as metal bridge, so the first term cancel each other, and what you are getting is basically the potential difference between the metal bridge in reference electrode beaker, with respect to your reference electrode, right? And that's why whatever electrolyte you're changing in your beaker, in your working electrode beaker, all the time what you're measuring is the same value. Now, what if you decide zinc as your metal bridge? Well, what is special about zinc is it does not care about your ferrous to ferric ratio, at least in 0.1 molar HCl. So in this case, you will not have a potential offset, or the potential of the zinc metal bridge in both the beakers will always be same, even if you change the ratio, and that can give you the same result as the conventional setup. And here is the result. As expected, yes, you are getting exactly the same result as you want to get. So yes, our simple equation does work. But now you might be wondering that why I'm talking about change in chemistry in both the beakers. Well, any electrochemical reaction would try to change the chemistry of your electrochemical cell, and same goes with our liquid cell TEM. Here is an example: iron going into iron 2 plus, and then oxygen reduction reaction, increasing the pH. So all such cases, may lead to a potential offset, because this reaction might not be happening in the beaker outside. So yeah, you might get some kind of potential offset. So how to avoid those potential offset? Simple solution. First, if you are using the continuous flow of the electrolyte, then you will never have this problem, because always you are flushing the electrolyte. And if you decided not to flow the electrolyte, then use a small surface area of working electrode, at least with respect to the volume of the electrolyte in your liquid cell TEM. All right, again, if you are still not happy with this, and if you want a big working electrode and really active metal as your working electrode, then at least know about the potential offset. If you know what kind of potential offset you are getting, then you can always subtract that value. Or if you still have the problem, then you can request Protochip to make another A chip with relatively non-polarizable reference electrode. All right. So yes, so here what you can see is in most of the cases, especially in corrosion experiment, you will have increase in metal concentration as well as pH. And using platinum as metal bridge, or using platinum as your pseudo reference electrode, you will have problem. As you can see here, both pH as well as ferrous to ferric changes the potential of platinum. But if you are using zinc as your metal bridge, then you would not have any such problem. Now let's try to understand why zinc works and platinum is giving us trouble in these cases. So here is the kinetic curves. Schematically, let's try to understand this. See, this curve shows the kinetic of oxidation and reduction reaction on platinum in this ferric ferrous redox coupled system. And if you the red point shows the open circuit potential of platinum in this system. And if you try to change the ratio, because of the shift in these lines, you will have different open circuit potential. But if you are using zinc as your metal bridge, then your dominating oxidation reaction is not oxidation of your ferrous ion. Instead, it is oxidation of zinc. And as you can see, the anodic oxidation curve of zinc is really flat. So any change in your ferric ferrous ratio or in pH, although it is going to change your corrosion rate, but it is not going to change your open circuit potential. So yes, this is a simple yet really effective concept. And if we understand this concept really well, we can extend the use of our metal bridge in different areas, including the places where previously we could not think of running any electrochemical measurement. So yes, if you need a really small reference electrode, or you need a leakless reference electrode, or wherever you are working with pseudo reference electrode, you can use the concept of metal bridge. All right, but as I said, in many cases you will not be able to have a flow system. So the change in chemistry and then origin of offset, potential offset, is really important. So you still need to understand or study the potential offset. And here are some results showing, if you have a situation where your pH might be changing, there are more alternatives for platinum bridge. So the graph shows you can use zinc, magnesium. In fact, you can use copper and nickel as well for a huge potential, a huge pH range. And in cases, for example, if you are interested in studying a pit, there you will be having change in chloride concentration, and it turns out in those cases zinc and magnesium can also not help you. And if you're using something like nickel or nickel alloys, they are relatively better. All right, so this okay, so a quick summary of the talk. So you can use the platinum pseudo reference electrode as your metal bridge, and use a true reference electrode outside your TEM cell. That will work really well. But yes, you need to worry about the potential offset because of chemistry change in your liquid cell. And if you're using a flow or using a really small surface area of working electrode, then you will not have any such problem. Applications outside the TEM electrochemistry, you can think of many more alternatives as your metal bridge. But again, there is a lot to do, and there is a lot to do, and we still need to fully characterize the parameter space where metal bridge can be quantitatively used. All right, so thanks for listening, and I'll be happy to have your questions. And I think this webinar will also be uploaded in Protochip website. So those who are watching me in future, they can also reach out to me using my email ID shown in this slide. And if you are really interested about the work, you can also read our recent paper published in Journal of Electrochemical Society. Thank you.
Thank you so much, Sanjay. That was a really great presentation, really great explanation of the leakless reference electrode. We were really proud and honored to be able to work with your team on this, and so thank you so much. I think we learned a lot from each other on this project, and excited to hopefully incorporate this. We'll be incorporating this into our Poseidon product to add some more flexibility to it. So we're really excited about that. I do have some questions here for you. So let's start going through them. And if we run a little short on time, then we can always connect you directly with those asking questions. Yeah. First one says, thank you for the presentation. Is the metal bridge wire completely exposed, or do you use a normal protected wire for your experiments?
Oh yeah, for most of my experiment, I used an insulated platinum wire, and then but their ends were exposed. But cases where I'm using really highly non-polarizable metal like zinc, then yeah, in other cases I was just using a fully exposed metal wire. That was also working really well.
Great. The next one says, thanks for the in-depth explanation. Have you considered radiolytic effects on the electrolyte due to the electron beam? This may change the electrolyte in the working electrode compartment drastically in comparison to the reference electrode compartment.
I think it is a great question, Jen, and probably you will be able to answer it better than me. But it is a great question. We haven't been able to explore that part. I mean, the effect of your TEM parameters, and I think the work is already ongoing. So we'll be able to get that answer soon as well. But right now, probably I'll not be able to answer the effect of radiation.
Sure, we can connect some of our applications engineers to you, Andreas, to help answer as well, because we've been doing some testing on this concept as well in the TEM with some samples that we're very familiar with. And so, right now, some of the main things that you're doing to minimize radiolytic effects, keeping a low dose, making sure you've got high flow to try and minimize that. But like Sanjay had explained, there could potentially be an offset, and this is something that you'll want to characterize and measure ahead of time, just in case there's a little bit of a change that happens throughout your experiment. And once you know what that offset is, you can take that into account during your measurements.
Yes.
The next question says, okay, so this may have just been answered essentially. Did you apply the reference electrode concept with the metal bridge within in situ experiments yet? And what has been your experience with it? Have you been doing in situ experiments currently, Sanjay, for corrosion?
Yes, 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 we are doing in situ experiment, although of course I can't share the results yet here, but as you can see, so I've shown the result, I think, which is the result what I showed is with our in situ experiment. But of course, with current setup in terms of TEM images, we can't see anything because with this system we don't have any precipitation or anything with this setup. But yes, we are currently running in situ experiment. But yeah, I guess I hope we'll be able to publish something soon.
Great. As for the user experience, we're working on something for that, where we'll have a nice accessory set up for the user to use with Poseidon, where you can incorporate this type of reference electrode and you don't have to build it yourself.
Yeah.
That will be very soon.
Yes.
So the next question, they're asking, how do you keep the liquid electrolyte on the surface of the working electrode inside the vacuum chamber of the TEM?
All right. Again, I think if you well, I think if you read our manual of the prototype, I think you will be able to figure it out. So in most of the cases, either we are we remove the layer and make it hydrophilic, and then I guess I think Jen, probably you will be able to answer it better than me. How to keep the electrolyte? Yeah.
Yeah, no, I can definitely chime in. So they're using our Poseidon system for electrochemistry in the TEM, and it's what we call a closed cell holder. And so what you're doing is at the inside the TEM holder, you're going to have two MEMS devices, and they're going to sandwich the electrolyte in between those two MEMS devices, and then you hermetically seal the tip of the holder by assembling it And you've got two electron beam transparent windows that go through those two MEMS devices for imaging. And so what you're essentially doing is hermetically sealing that environment so that when you insert the holder into the TEM, the vacuum is not affecting that environment. And so it's an enclosed cell, and so you're able to flow electrolyte through. You've got the electrodes patterned on those MEMS devices. You have all the electrical built into the holder. And so they're using that Poseidon holder from us to, as they continue their in situ experiments in the TEM, to maintain that electrolyte at the electrodes, and you don't have it freezing or evaporating off or anything like that.
Yes.
We have a couple more questions and then I think we'll be able to wrap it up. So thank you for the great talk. You really explained the concepts well. I was wondering about how you assess the stability of the metal bridge in an electrolyte. For example, zinc was stable in the electrolyte shown, but how much dissolution is acceptable?
That is a great question. That is a great question. I think, quantitatively, I'll not be able to answer or I'll not be able to give any result yet, but I think that is a section we are still studying. And in cases where if the dissolution of metal bridge is affecting your electrochemical reaction of interest, then of course it would be a problem. But cases where using just platinum, then you don't have the dissolution related problem. I think that is an area where we still need to do little more work, and we need to have a metal bridge where any dissolution should not be affecting our electrochemical reactions of interest.
Great. And there was one follow-up question, which I'll go ahead and ask since we've got a couple minutes in case there's other people wondering. If you've got any other questions, everybody go ahead and enter them in now, because this is the final one that I have so far. Same person who was asking about how you keep the electrolyte on the surface of the working electrode inside the vacuum. Their follow-up was asking about, do the transparent windows in the MEMS devices affect the transmitting of the beam and the results? And I can start, Sanjay, and if you have any experience that you want to add, please feel free. Of course.
You can go.
Sure. So the what we call windows that allow the transmission of the electron beam are an amorphous silicon nitride. They certainly can affect the transmission of the beam, meaning as you're going through the windows and you're going through the liquid, you're going to have some scatter of the beam, primarily because of the liquid more so than the windows. We've got a lot of great results in gaseous layers with the windows at high resolution and such, but you will definitely have some scatter from the liquid. A lot of people like to use STEM mode instead of TEM mode, which helps them also control the dose, which will help control radiolytic products as well. And so you do want to try and have the thinnest liquid layer that you can. That then you then have to balance how thin your liquid layer, which is your electrolyte, is, so that it doesn't affect your electrochemical results, because the thinner you get, the faster you'll have depletion of ions and such. And so there's definitely some optimization for the experiments that you need to do. Like Sanjay's doing a lot of work outside of the TEM to start to make sure everything is comparable to traditional types of electrochemical experiments. We have workflow items to help with this, like what we call the ex situ cell, which is a replica of the holder tip that you can use outside of the microscope. And then as you introduce your system to the microscope, you're starting with low doses, you're doing more comparison results to make sure that the beam is not having an effect. There's lots of publications on batteries, corrosion, catalysis using this in the TEM, and I would be more than happy to share with anybody who would like. You can just respond to your email for this webinar and just request a bibliography, and we'll be happy to share. And you can see how people do these tests for their publications on how to ensure that they feel the results are relevant and their confidence in that. Sanjay, feel free to add anything you would like to with some of your experience if you care to.
Oh yeah, I mean, I think that is a great explanation, and I don't think I'll be able to talk anything about the characteristic of the nitride window. Um, yeah.
No, that's great. And then I just had a question for you that I thought might be interesting. Would you imagine that this metal bridge would work with non-aqueous electrolytes just as well as it does with aqueous electrolytes?
Ah, that is a great question. Again, I would say probably at this point, I might not be able to answer that question, but seeing our concept, seeing the simple equation, if that goes and that should work with almost everywhere. Um, it is just connecting electronically connecting two beakers, right? So in theory it should work, but as I said, I think non-aqueous solution, yeah, we still need to um, think little more into it.
Sure, sure. We did have one more question come in that I thought might be interesting to the crowd here as well. So let's go ahead and slip that in, and then we can, say our goodbyes. So thank you for the nice lecture. I was wondering if the ohmic drop due to the distance of the reference electrode could be a problem.
Oh yeah. So of course, if you are using a non-conducting or less conducting electrolyte, you always worry about the distance from distance between reference electrode and your working electrode. And because here we are using the wire as our Lugin probe, so you can go as close as possible. So the metal bridge end in your working electrode cell, you can go very close to your surface, and it will avoid any such IR drop, and that's where we call it metallic Lugin probe. And the idea of Lugin probe is to reduce the IR drop. So our metal bridge concept does work, reducing IR drop.
Great questions. All right, so I think we've actually made it through the list today. Sanjay, thank you so much for your presentation. It was fabulous. I think we all learned a lot from it, and it's been so nice collaborating with your team, you and Professor Kelly as well, because we've got a lot of microscopists on our team. You guys are the electrochemists, and so I think the combination of us together really helps us develop some new concepts that work for both fields. So thank you so much for everything.
No, thanks a lot, Jen, for this nice collaboration. I think this was a really great opportunity for us to explore the unexplored area of electrochemistry, and you can see what we have got is a really big deal. And yeah, we really hope that people watching us or in future can use the concept of metal bridge in their experiment, and they can get excellent result, which was not possible with our conventional setup.
Yeah, absolutely. We want more electrochemists to see the value in this technique because we think it's very important, but the importance of being able to compare it back to bulk scale results is just, it's not comparable. Like you cannot ignore that. And so our goal is to try and help compare the nanoscale with the bulk scale with relevance and confidence for everybody. So I think this is a great step in that direction. So thank you again. Thank you everybody for joining, and if you have any additional questions, feel free to respond to the email and I'll connect you with Sanjay. And I hope everybody has a great day, evening, night, morning, and we'll see you all soon.
Bye-bye.